Hello everyone, today we are going to understand what are priority queues and what are heaps because they are related to each other but they are not the same. And priority queue is one of the most asked patterns in DSA interview questions, so it becomes a really important topic for you to understand. So let us start by understanding what is a priority queue. A priority queue is nothing more than an abstract data type. It is a simple ADT, abstract data type. What this means is that a priority queue is not really a data structure, like there is no implementation for priority queue as such, but it is basically a set of rules. That's what this abstract data type means. It is a set of rules that actually defines the behaviors that we want. And the rules are very simple. To be honest, there is just one rule that you need to understand, and that is the top element in this priority queue or the first element in this priority queue should be of highest priority. What this means is that the highest priority element should be easily obtainable. We should be able to get this element in the lowest time complexity. But here the question arises, what is exactly a priority? Well, a priority is just a number. Okay, it's going to be 1, 2, 3, 4, 7, 9, whatever it is. It is going to be a number that actually denotes the priority of the item. For example, we can have data like this: 1, Raj. We can have these kind of items inside of this priority queue. Now this number 1, this number 2, and this number 3 is going to be treated as the priority. They are going to indicate what is the priority for this particular data, Simran. What is the priority for this particular data, Raj? What is the priority for this particular data, Juice, right? And then it will be up to us to decide whether the 1 will represent the highest priority or will it represent the lowest priority. Will 3 represent the highest priority or will it represent the lowest priority? And that will be on our part. Do we want to say that 1 have a higher priority than 3, or do we want to say that 3 have a higher priority than 1? That is our decision. And based on these two decisions, we will end up having two types of heap that we are going to understand shortly. And this is pretty much it. This is the priority queue. It is an abstract data type, which simply means it is a set of rules. And one of the most important rule is that the top element or the first element in the priority queue should have the highest priority. Now, whether a lower number have a higher priority than a larger number, that is depending on our choice. We can set that, we can decide that in the priority queue. But the top element or the first element must have the highest priority so that we can get this number or get this element as quickly as possible. Now understand that priority queue is just an abstract data type. It is a set of rules, right? It does not really have an implementation. It is like me telling you that, hey, I want something that have four circular things, okay, that can move from one place to another place, that can basically make a sound if I want someone to get out of my way, that can actually help me play music, that can actually connect to the internet also, that can do something like accelerate and decelerate. These are my requirements, right? I'm telling you that, hey, I want something with these kind of specific behaviors or specific properties. And it turns out that a car actually implements all of these rules that I talked about, right? You can go from one point to another point, you can accelerate, you can decelerate, you can play music, right? You have these four wheels, the four round circular things, right? You have all these rules satisfied with the help of a car. But just think about it, right? It's going to be a real car with a real engine, okay, but you can also implement the same functionality with a toy car, right? A toy remote control car also implements all of these functionalities. So the way you implement these functionalities can differ. Okay, these are basically the implementation, the toy car, the real car, their implementation of the rules or the behavior or the properties that I just specified, going from one place to another place, right? Then playing music, then being able to honk on other people, right? So all of these are basically just rules, and these two implement these rules. They can implement them. But let's be honest, when we are talking about these rules, we are not really talking about the toy car, we are just talking about the real car mostly, right? It's like an implicit thing. And I believe you can guess now, the heaps are basically the implementation for priority queues. So priority queue is basically a set of rules or set of requirements, and heap satisfies those requirements. Heap is basically a data structure, a real implementation of priority queue. Now heaps are not the only implementation. We can implement priority queue with the help of an array also, or a list also. So suppose that we have a list like this, L is equals to like this, okay? Then we have a, let's just say, and now in terms of priority, let's just say the smaller element have more priority than the higher element. It means the first or the one actually have the highest priority. So this particular thing, this particular array also satisfies the priority queue right now, right? Because we can take this element fastest. It is going to be order of one time complexity, right? But understand that this array is right now sorted. it doesn't need to be sorted, right? What if we had a 6 here instead of 1? In that case, we would actually have to go through each and every element here on this list, and then we will have to find out the element with the maximum priority. In this case, it is 1, then we will return the 1, correct? But this going through entire list, then taking out the element, it is going to take order of n time complexity. Do you understand this thing? So it is having an order of n time complexity to get the element we want. And now if I want to insert an element like 7, I want to insert 7, I can simply take this element and place it at the back, right? So after 5, I will have 7 here. So basically, the time complexity for insertion is order of 1, and time complexity for extraction or finding the element is order of n, correct? And that is in the case of unsorted array. Now what if this is sorted? What if we have an array like this, or a list like this? We have 1, 2, 3, 4, 5. Okay, we have this sorted array or sorted list. So it is going to be sorted always, right? Here you can get the element with the highest priority first easily, because it will always be the first thing in the list, right? So you can easily get this out, and getting it out will be order of 1 time complexity. But inserting something, if you want to insert, like I say, I don't know, like I say 3.5, then you will have to take this thing, place it here, right? And if you want to place it here, you will have to take all these elements and shift them by 1, and that will take order of n time complexity. So it means the insertion is order of n at this point. Here the extraction was order of n and the insertion was order of 1, and here the insertion is order of 1 and extraction is order of n. So it basically just flipped. It doesn't really give us anything useful, right? And yes, even though you can implement the priority queue with the help of these array or these kind of solutions, they are definitely not optimal. We have order of n time complexity. We can do much better. And we can use heaps to do much better. And that's why we are going to use heaps to implement the priority queues. So now let us understand the heaps. We basically have two types of heap, min heap and max heap. But before we go to them, let us try to understand what exactly is a heap. So a heap is a simply binary tree, or BT. That's it. It's just a binary tree. But this binary tree actually implements a specific property. But before we understand that, what exactly is a binary tree? A binary tree is basically a tree in which we have a node and we have two children of that node. Okay, we have one children, we have another children. This is the left children, this is the right children, and this is the parent node. That is a simple binary tree. So we can have a tree like this. One node here, one node here, then one node here, then one node here, then one node here, right? So we can have a tree like this. Here, this node actually have these two children, and this particular node actually have these two children, right? Similarly, this node have these two children. So each node actually have two children, and 2 means binary, and that's why we actually call it a binary tree. Now this binary tree is basically like a base tree, a raw material that we can use to generate many different kind of things. We have a binary search tree, we call it BST, and that binary search tree is basically a binary tree. It just implements a property that, hey, this parent node will have a value greater than the left node, so it will be like this, and this parent value is going to be less than or equal to the value in the right node. So suppose that we have a 3 here, so it means it is important that we have a value less than 3 in the left node. So I can write 2 here, or I can write 1 here, right? So suppose I write 1 here. And then on the other hand, in the right child, it is important that I will have a value greater than or equal to 3. So I can write 3 here, or I can write 4 here, or I can write 10 here. But I cannot write 2 here because 2 is not greater than or equal to 3. So that's why I need to write something like 4 or 3 here. And now this has become a BST, or binary search tree, because it is implementing a particular property or particular rule inside of it. And this is exactly what we are going to do to construct our heap also. So heap also have a property that we are going to implement inside of this binary tree. A binary tree is like a white paper. It's like a canvas in which you can actually draw whatever you want to. So now let us look at the min heap first. The max heap is basically the opposite of the min heap, so it will not be hard for you to understand what that is. So for min heap, we have this particular property or a rule. Each node must be less than or equal to both the child nodes. What this means is that we can have a binary tree like this. We will have, like just say 5 here, okay? And then in both of these child nodes, the value should be greater than or equal to the parent node. For example, I can write here 6, I can write here 10. So this is a condition for min heap. The each node, that means this one node, the fifth node must be less than or equal to both child nodes. So for fifth node, we have this 6 as child node, 10 as child node. So 5 is less than this child node and this child node. So it is actually satisfying the min heap property. But then how do you actually construct a tree like this? Well, for that you need to understand one thing. How we represent a tree inside of an array. We have a list like this, okay? And here we can have like just say 5, 7, 9, 8, like just say 12, okay? So these are the nodes that we have. Now in an array, we can represent a tree like this. We have a parent node, okay? And the index of the parent node is I. Then the index of the left child node LC is going to be 2 multiplied by I plus 1, and the index of the right child node is going to be 2 multiplied by I plus 2. So if I try to make a tree with these data, it will be something like this. We will have indices like 0, 1, 2, 3, 4, and now we can start making it. So first of all, the I will be 0, right? So I will take the fifth node like this, and now we want to figure out the left child node and the right child node of this fifth node. So the left child node is what? 2 multiplied by I, that is index, plus 1. So 2 multiplied by 0 plus 1 is 1, right? So it means the index 1 represents the left child node. It means the 7 is going to be the left child node. So we will draw it like this. In the same way, to find the right child node, we will do this. 2 multiplied by I plus 2. So 2 multiplied by 0 plus 2 is what? 2, right? So the index 2 represents the right child node. It means the right child will have 9 here. Okay. In the same way, if I want to figure out the child node for 7, so the index for 7 is what? 1. So the left child node for 7 is going to be 2 multiplied by 1 plus 1. So the third index is going to represent the left child node for this particular 7th node. So we will have like this. We will have 8 here because 8 exists on the third index. In the same way, I can figure out the right child node also. So 2 multiplied by 1 is going to be 2 plus 2. So the fourth index is going to represent the right child node for this particular node. Now if I try to find out the left child for 9, I will multiply 2 by 2. So 2 multiplied by 2 is equal to 4 plus 1 is equal to 5. But we don't have a fifth index, right? We don't really have it. It means that ninth does not have any left child. And if I try to find the right child, I will have to multiply 2 by I. So 2 multiplied by 2, 4 plus 2 is going to be 6. We also don't have 6. That means we don't have any right child for 9 also. And in a similar way, we don't have any left child for 8 or right child for 8. We don't have any left child for 12 and right child for 12. So I hope you can understand how we are able to represent a simple binary tree. It is not a heap right now or a BST right now. It is a simple binary tree with the help of a list like this. And now we have all the information we need to create a heap. So now suppose that we have a list like this. We have 9, 10, 1, 3 and 2. And we want to create a heap from this list. So what we can do is we can take the first node, okay, and we will just write it like this. We will have it in the heap like this. We will just store it. So we will actually have this heap a list here. Inside of it, we will keep on storing the nodes, but I'm not showing it here like this explicitly. I'm not showing everything visually. So we will have the 9 here, and now we will get the 10. Okay, so the next thing is 10. 10 is what? 10 is greater than 9, right? So the first instinct will be to actually create the left child node for the 9. Since 10 is greater than 9, we will simply create a left child node for the 9. What this simply means is that we will have a 9 here and then we will directly add 10 here. Simple as that. Okay, that's what it will mean. Now we will actually get this 1. And now here the things get tricky because 1 is less than 9. So I cannot just go ahead and place it like this here. It will be wrong, right? But that is exactly what I'm going to do. I'm going to take the 1 and I'm going to place it here. Okay. And then I'm going to use a function like shift up. Okay. We will create this function in the code. Don't worry. But we will use this function on this node. Okay, and we use this function to make sure that this particular one is going to be on the correct position. So what this shift function actually do is that it will take the current node, that is 1, and it will check the parent. Now how do you find the parent of a node in this particular heap list, right? Well, you will have the index of this one node. Okay, now to find out the parent, you will simply do this. Parent is equals to I minus 1 divided by 2 floor function. Floor function simply means that if the result of I minus 1 divided by 2 is something like 2.5, you will round it off to only 2. That means the parent is going to be 2 if the answer is 2.5 here. That's all the floor function means. And do not worry, you do not have to implement this floor function yourself. In each language, you will have a mathematical library that will have it for you already. So now in the shift up, what we will do is we will take the index of the 1. Okay. So basically we will be placing 1 here immediately after the 10th. And then we have the I is equals to what? 2. So I right now is 2. Now to find out the parent is 2 minus 1 divided by 2 is equals to what? 1 divided by 2 is equals to what? 0.5. And then the floor function of 0.5 is what? 0. It means the parent is going to be on the 0th index, which is 9, right? So 9 is the parent. And now we will check just one thing. Is this current one node less than 9 or not? If it is less than 9 or basically less than the parent, we will swap. We will take this one node and we will take this ninth node and we will swap their position. Okay. So we will also have to create a swap function that will take two things, two value 1, value 2, and it will simply swap them. And do not worry, we will see this swap function implemented in the code. So here I will just take the 1 and 9 and I will simply swap their positions. So 9 is gone from here, 1 is gone from here, and then we will write it like this. 1 will be here, 9 will be here. So we have swapped the elements. Now 1 is less than 10 and 1 is less than 9. So it means we are again satisfying the min heap property that each node in the tree will have less value or equal to value than the child nodes, not more than them. Now we will take the next element, that is 3, and we will insert it inside of the heap. So we will simply add it at the end. So 3 will come here, and now we will check, is it actually making sense? So what is this 3? Where will it be? Well, the index of 3 is what? 3, right? So what is going to be its parents? Well, 3 minus 1 divided by 2. 2 divided by 2, that is 1. It means the element at index 1 is going to be the parent. So the element at index 1 is what? 10. It means 10 is going to be the parent and it is going to be the left child node of 10. That is 3 will be here. Now we see that the 10 is more than 3 and 10 is the parent here. It should not be the case. It is breaking the min heap property that each node is going to be less than or equal to its children. So we are going to use shift up again on this third node. So we will take this 3 node, we will calculate its parent and we will swap it. So after swapping, we have 3 here, we have 10 here, just like we have in the heap array. Remember, I'm using the drawing of this tree for visualization. Okay, in the memory, in the computer, this list is going to be stored in the computer. Now we reach the next element, that is 2. So we will try to place the 2 here. We will expand this list and we have 2 here. Now where will it be? Well, the index of the 2 is what? It is going to be 4, right? And so the parent is going to be 4 minus 1 divided by 2 floor function, which means 3 divided by 2 floor function, which means 1.5 floor function, which means 1. So 1, that means this particular node, the 3 node is going to be the parent of this 2 node. It is going to be the right child of 3 right now. So we will have 2 here. But you can see that it is breaking the heap property. So 2 is less than 3. But it should be the other way around because it is a min heap. It is a min heap. That's why we need 3 to be the child of 2, not the other way around. So we will again use the shift up function and we will simply swap these two elements. Now after swapping, the tree will look like this and we don't have any other elements anymore in the given list. And our heap looks like this: 1, 2, 9, 10 and 3. And this is how we are able to build a min heap. So now we are going to use the same heap that we created above and try to extract the element from it. So we know that the top element is going to have the minimum value, and here we are saying that 1 is greater than 5 in terms of priority. That's why it is a min heap. So it means 1 have the highest priority, so it is at the top. So what we are trying to do is we are trying to take this element out 1 and then reheapify or basically recreate this entire thing in as less time complexity as possible. So what we will simply do is we will say element that we want to get is lm. Lm is equals to what? Heap 0, because we know the highest priority element is always going to be at the 0th index. So we have the element now and we just have to remove this from this particular place. So how do we do this? Well, if I just go ahead and do this, I just try to remove this from here, I will have to take all this element and shift them this side, right? And it is going to take what time complexity? Order of n. That will be order of n time complexity, but we don't want that. If we wanted that, we would have used the sorted or unsorted array anyways, right? So what do we do now? It is very simple, guys. We will take the last element and we will override 1 with 3. And to remove the last element is very simple. We will simply remove it. We will use function like pop, or basically we will just override it with 0. Okay, removing the last element is basically order of one time complexity in any language. But now that we have placed the 3 here, we need to make sure that the heap actually satisfies the property properly. So right now we have 3 here, and we have removed this last element from the heap. So as you can see here that this 3 is basically greater than this child element. But that should not be the case for min heap. For min heap, each node should have greater child than itself. So it means we are not satisfying the min heap property. So now we have to use something like shift down. Okay, shift down is actually a function that will help us make sure that this tree is again a heap. So we will run the shift down on this particular node, and we will need two things. First is left child, which is going to be what? 2i plus 1. And then we need right child. It is going to be 2i plus 2, right? Now we know that the index of this particular node is what? 0. So what is going to be the left child? Well, 2 multiplied by 0 plus 1, 1. In the similar way, 2 multiplied by 0 plus 2, it is going to be 2. So left child is going to be at index 1 and right child is going to be at index 2. Okay. So after finding out the left and right child, we will take the minimum of these three. We will take this element, we will take this element, and we will take this element, and we will make sure that we actually get the minimum of these three elements in this top position. So first we will check, is the element at index 0 greater than the element at index 1, that is 2. If it is greater than, we will simply say that the min element is at index 1. Okay, this particular index. And now that we have the min index 1, we know that the value at min index is 2, right? This particular 2. And then we will actually make a comparison between this 2 and this 9. Okay, we are not going to make a comparison between 3 and 9 because we know that 3 is basically greater than this element. So we need to make sure that this element, the 2 element, is also less than this particular right child element. So if I make a comparison, then I realize that yes, 2 is less than 9. So the minimum index will stay 1. If in case this was not actually 9, suppose if this was actually 1, if this was 1, we will see that 2 is greater than 1, and we will have to change the minimum index or update the minimum index to basically 2, the index 2, because this particular node will be at index 2 in the heap list. But currently it is not 1, so we will not do that. And now we have the index at which we have the minimum element. So what we will do is we will take the element at this index and we will swap it with this particular 3. So the index is 1, that means 2. So we will take the 2 and we will swap it with 3. And now after swapping, we have 2 here and 3 here. And now we will run the shift down function on this node because we want to make sure that this particular subtree is also a min heap. Okay, so that's how we are going to do. And here I can see that the 3 is greater than 10 and this particular thing does not exist. So it is already a min heap. So we don't have to do anything. We can stop right here. But if it was something like 2, we will actually have to do the same process again. Get the left child, get the right child, find the minimum index, and then we will swap them again. And so we will keep on calling this shift around function until we make sure that we have the entire subtree as a heap again. Now we can go ahead and see the operation versus time complexity. So for insertion, we actually have a time complexity of log n. And this is because we have a tree like this. We have node here, then again node here, then again some node here. Okay. And we are actually inserting something at the last index here. And then we just bubble it out, top and then top. We are not dealing with every other element here. We are going to be running the shift up function from this node to the root node, and that is going to take log of n because we are not going through every element here. Similarly, to remove an element from the top, we will use the shift down function, and the shift down function will also just go on a particular path only, and that will also take order of log n because we are not going through each and every path. If we were going through each and every path, we would have gone through n elements and nodes, but we are not going through each and every path. We are going to specific path. Now here is the tricky part. If you have an array like 1, 9, 7, 8, okay, and you want to build a heap out of it, in our current implementation, it will take order of n log n because you will keep on inserting the elements in the heap, and you are inserting n elements, and each element will take order of log n time complexity. So it will take order of n log n time complexity to build a heap from a given array. But in languages, okay, you have a much better, more optimized solution. So there you will actually just take order of n time complexity to build a heap from a given array or a list. So in our current implementation, it is order of n log n, but the implementation that you will be using from your languages, it is going to be n. And the proof of this order of n time complexity is actually quite mathematical. So I will not be going in that proof, but you can search online if you want to dig deeper in this concept. Now the max heap is identical to the min heap. It is basically the same. The only difference is the property. So here each node value is greater than or equal to the child nodes. Basically in min heap, parent was actually less than or equal to child nodes, but in max heap parent is greater than or equal to child node, and that means the only thing that will differ is this particular sign. In the max heap we will use the greater than equal to sign, and in the min heap we are using this less than or equal to sign to actually implement the shift down and shift up. Everything else will be same. All the implementation, all the logic, all the time complexities are going to be the same. They will not change, and you will see that very clearly in the implementation that I'm going to show you for max heap and min heap. Believe me guys, they are the same. Even in implementation, the only thing that will change is this particular sign from less than to greater than. So here is the implementation of min heap in Python, just to make sure that we understand everything easily. First of all, we are creating this heap array or heap list in which we will store the heap, and we are doing this in the constructor so that each time we create an object of min heap, this particular array or this particular list will already be initialized. It will not be null or none. And then here we have a few functions. This function tells you the parent of the given node I. So we will have the index of the node, we will pass it in the function, and we will get the index of the parent. Okay, here we are using the I minus 1 divided by 2. This particular sign says integer division. So it means if the answer of this expression is actually 2.5, we will actually get 2 here. Basically the floor function that we talked about. And then here we have the function to get the left child node. As you can see here, 2 multiplied by I plus 1. We are returning that index. Here we have the function to get the right child node. 2 multiplied by I plus 2. So here is the swap function. It's a very simple function. We will have the I, we will have the j, and then we will simply swap the elements at I and j with the j and I. It is a simple swapping function, and yes, in Python you can do this. Okay, this line is only valid in Python, but if you are using something like C# or Java, you will have to use the temp variable to store one of these elements and then just make the swap that way. Now here is the function that inserts a particular element inside of the heap. So we will take the element or the key that we want to insert in the heap, and then we will take the heap, and then here in the heap array we are appending or we are adding this thing at the end. So append function will take this particular given input, the key or the element, and append it at the end of the heap, just like we were doing in the drawing explanation. Now once we have the key at the end of the heap, we will use the heapify up or shift up. So this is basically the shift function that we talked about. It is heapify up or shift up, you can call it whatever you want. But this function is going to do the same thing that we discussed. Here we are giving it the index at which we appended the key, which basically means that we are giving it the last index that is currently existing in the heap, and then we are running this particular heapify function. So what does this heapify function do? Here it is. It is going to just run the while loop just like we were doing. So what it will do is it will make sure that the index is greater than 0. It is not basically less than 0. If it is negative, we have reached the top and we have gone out of the bounds. So at that point, we will simply stop the while loop. But here is the main condition. Here we are checking if in the heap, the parent of this particular given node I, if it is greater than the current node's value, the value at the current index I, then we will simply swap, because we want to make sure that the parent is less than, but it is currently greater than this particular ith node. So we will simply swap the ith node with its parent, and then we will set the I to its parent's index, and then just keep on using the while loop until we make the entire tree a heap again. Now here's the function that will remove the node with the highest priority. Here also what we are doing is simple. We have a few checks in the starting. First of all, if the self.heap is none, it means it doesn't exist. Simply return none. Okay. Then we are checking if the length of this particular heap is 1, that means there is only one element. We will simply pop that element. It means the heap at this point is empty. Simple, right? And we will just return it. But in any other case, we know that we will have to re-heapify or basically reconstruct the tree somehow. So first of all, we will get the root element or the element with the highest priority in the root variable, just like we did in our drawing explanation. And then we will take the last element in the heap, we will pop it, and then we will take that element and we will override the top element or override the top position in the heap. That's what we are doing. And now we are simply using the shift down function or heapify down function to make the tree a heap again. And in the heapify down function or the shift down function, we are doing exactly the same thing that we discussed in the drawing explanation. We are getting the min index, we are setting it to I right now because that's what we know, that I is the minimum right now for us. Then we are taking the left child, we are taking the right child, we are taking the length of the heap so that we will not go out of bound. And here we have the checks. So if the left index is less than n, that means we are within the bounds of the array or the list, and the value at the left index is less than the value at the current minimum index, we will change the minimum index to left. Simple. And then we will check again if the right index is less than n, which means we are within the bounds of the list, and then we will check if the element at right index is less than the element at the current minimum index. That means even after updating the minimum index here, we are again checking it with the right element. So it means the element at the right index is still less than the element at the minimum index. Then we will simply update the minimum index again, and then we will check if the minimum index is not basically the same as I. Then we will simply swap I with minimum index, and we will just again call the heapify down function on this new minimum index. We are calling the heapify down function on this new minimum index. It's a recursive call. If it is not true, that means we have made sure that the current heap is a min heap again, and we will simply exit this function. And then here we have a simple example usage. So we will simply create the object of this min heap class, and we will have some elements like this, and we will just keep on inserting these elements inside of the min heap easily. And once we have the min heap, we are just printing something, and that's all. You can use this as an example code to test things out on your end. And here is the example for max heap. It is literally the same as min heap. We have the constructor here. We are again initializing an empty heap here. We have the functions for calculating parents, for calculating left child, for calculating right child, and then we have this function for swapping also. Then we have this function for insert also. It is basically the same as earlier function. And then we also have this function for extracting or removing the element. It is also basically same as the earlier function. The only difference is this heapify up and heapify down function. So in case of min heap, the only difference was that this particular sign was actually like this. Okay, and we just flipped the sign to this. So right now what we're saying is that the parent element, if it is less than the current element at index I, we are going to swap. We are just doing the opposite of what we did in the min heap, and the rest of the function is basically the same. Same for the heapify down. Here we are checking this particular thing. We are checking if the element at left index is greater than the element at max index. If it is greater, we update the max index, and then we are checking if the element at right index is greater than the current max index. If it is greater, then we will again change the max index, and here we are checking if the max index changed. Then we are simply swapping, and then we are again calling the heapify down on the max index recursively. It is basically the same thing. The only thing that we are changing are these signs. That's all. And here's the code for example usage here. So you can create a max heap object, then you will have some list of elements, right? And then you can simply insert all of those elements with the help of max heap.insert function. Then you can try to print everything down if you want to. You can use this example code to test out your max heap implementation also. Now, one tip that I want to give you is that you will use the heaps or priority queue for these kind of questions. The top k elements or the top k greatest elements. Basically, you will have a condition and you will have to find the top k or the most useful or the most important k elements from the given elements for that particular condition. And there you will use the priority queue or minimum or maximum heap depending on the question. I have already created the videos in which I am solving these kind of questions with the help of priority queues. So you please watch them if you want to get a greater understanding of it. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.